The Hertzsprung-Russel diagram. In this video, I will be explaining the Hertzsprung-Russel diagram. Before I start, what do we actually even need to know about this? Well, according to the specification, we need to be able to recognize and use a simple Hertzsprung-Russel diagram to relate luminosity and temperature. We also need to be able to use this diagram to explain the life cycle of stars. It seems pretty straightforward, but firstly, what even is the life cycle of stars? Well, simply put, the life cycle of stars just shows the different stages in stars' existence from birth till death. And the model looks a little bit like this. It all begins with a stellar nebula, or as we know it, the protostar. It's kind of like the mother, and basically it's a very strong gravitational pull causing matter to condense. From then, either an average star or a massive star are born. It all depends on the size of the stellar nebula. The average star then starts to undergo nuclear fusion, forming helium from hydrogen. After many, many billion years, the hydrogen fuel is eventually going to run out, and that's when it forms a red giant. Now, a red giant is a lot less stable than the average star, and its lifespan is a lot shorter. It then forms a planetary nebula, which pretty much really quickly forms a white dwarf. The white dwarf lasts very long. In fact, it is hypothesized that the white dwarf will eventually fade off to form a black dwarf. However, the time span for that to take place is longer than the existence of the universe itself, so no black dwarfs have ever been observed, and it remains a theory. Now, if a massive star is born, it takes a different route. A massive star undergoes nuclear fusion as well, but it does so a lot faster. It really quickly runs out of fuel, forming a red supergiant, and the shells from the red supergiant keep being formed, and they keep pressing up against each other. This eventually leads to a giant explosion we know as the supernova. It is so massive, in fact, it is the biggest explosion that takes place in space. And the supernova actually is kind of the birth of black holes and neutron stars. It's what causes them to happen. We don't know much about black holes or neutron stars because they're extremely powerful as they are products of supernova. But what we do know is that the black hole's gravitational pull is so strong, even light can't escape. What are the fundamental differences between a low mass star and a massive star? Why do they have to take such different routes? They have completely different life cycles. What causes them to be that way? What are the differences between them? Well, the main cause for the change of the life cycle is basically the rate of the nuclear fusion. Now, they both undergo nuclear fusion and they both turn hydrogen into helium. However, the massive stars go at a much, much faster rate. Therefore, that leads to the fact that low mass stars takes billions of years before it runs out of fuel. Our sun is estimated 5, 6 more billion years, which leads up to almost 10 billion years before it runs out. Smaller stars actually can go up to 100 billion years before they run out of hydrogen. However, massive stars take just around 1 million years before the fuel runs out. So it has a very short lifespan. Low mass stars are produced from a smaller protostar, while massive stars are produced from a large protostar. Now, low mass stars are more common since it is a lot easier to form a smaller protostar and an average sized protostar than it is to form a large protostar large enough to form a massive star. In their lifespan, low mass stars burn a lot less bright than massive stars. And when they burn, they burn different colors. You see, a low mass star burns an orange-red color, while a massive star burns at a blue color. In fact, it gets so hot that it has edges of white sometimes. A low mass star simply dies by just fading off. It goes into a red giant, and then a planetary nebula, and then the white dwarf, and a black dwarf. It just fades off each time. While a massive star goes with a bang, it goes in a giant explosion known as the supernova. The main example of a low mass star that we know and we see every day is our very own sun. And as you can see, most of its shining is like most of its light is orange with bits of red, and its very hot areas are barely yellow. However, the most common example of a massive star is the Wolf-Rayet star R136A1. And if you see it, it's blue. In fact, it is so hot in some areas, it's burning white, and it burns very, very bright. Now we can finally move on to what is the actual Hertzsprung Russell model. We know that it helps us classify these, we know how it helps us identify where they are, but what is it? Luminosity against temperature. Basically, a couple of guys just plotted star luminosity against decreasing temperature, with star luminosity on the y-axis and the decreasing temperatures on the x-axis. And they've realized that it shows an overall negative correlation, and they came up with this model. Most stars we observe would fall on a diagonal line across the Hertzsprung-Russell diagram, which is called the main sequence. There are stable stars that will exist in this state for the majority of their lifetime. As we can see, the higher the temperature, the higher the luminosity, as temperature is decreasing on the x-axis. However, there are also other stages in a star's evolution which appear in other places on the diagram, but these are much shorter than its stable period. Therefore, there are far fewer stars in the parts, for example, for the supergiants, and they burn out just a few million years, and so they've already done so, so we don't even see many, and it's very underpopulated. For example, the supergiants and the giants have a high luminosity with very low temperatures, and they die out really quickly. And the white dwarfs have a very low luminosity and a very high temperature, but it in fact takes a really long time to form, so we don't have many of it. And these areas remain lightly populated, especially in relativity to the main sequence. Now, nothing is perfect, so there are problems with the model. The main problems with the model fall behind taking the actual results. So temperature measurements are assuming that the bodies behave as black bodies, which we know is not the case. We know that the temperature with stars fluctuate, but it's the only way we can have a stable enough measurement to use. Also, the biggest problem comes behind luminosity, as luminosity is calculated using distance, and calculating the distance of the star isn't very valid. There is no actual scientific method of calculating distance of the stars to us that has been brought up to the table yet. And if there are methods that do exist are very invalid and not really accurate, and that leads to luminosity being not very accurate. But the model may have some problems, but the trend there is undeniable. So in conclusion, the model plots luminosity against decreasing temperature, and it showed the different stages of the life cycle of the star. You can see that the different life cycles and how long they take, and that they're very much less abundant than the actual main sequence, which, by the way, showed a negative correlation. And the last point is that I am awesome. So thank you. I hope this helped you understand what the model is all about and how you can use it to identify the different stages of a life cycle of the star. Thank you.